All right, good afternoon. Let's start lecture, okay? Okay, so let's finish a little bit on controllability, stability, and then we'll go into another topic called pole placement, okay? Quickly review on the controllability and the observability. If you have a discrete state space model, then the controllability matrix, which is this one, and the observability matrix, which will be this one here, okay? Yeah. The rank for both of the matrix needs to be full in order to have a controllability or observability. Okay, so basically this one I think we call that CO matrix, AOB matrix, right? We're looking at the condition is basically the rank of CO is n, and then also the rank of OB is n. And that's the condition for either controllability or observability. Just a little bit on the observability at here, because this is this is in the column format at here. Okay, in the column format. Now, you could also, instead of the column format at here, so basically the condition at here, you can also write is the rank if you take a transpose of the matrix. So instead of looking at the rank of this matrix, you can also look at the transpose, the rank of the transpose of the matrix, which will be equivalent. Okay? Yeah. So what's the transpose of the matrix then, right? This essentially transpose of a column vector, right? It's a column vector, but this is not a single column vector. It looks a column format, but of course each one has a row there, right? So the the transpose is basically you're gonna transpose this whole column vector will become a row vector, and then you're gonna have to take a transpose for each individual element at here. So what you end up with is a C transpose at here, and then CG transpose, and then up to CGN to the power of negative n minus 1 transpose. Okay, that's the transpose of this observability matrix, right? So column becomes row, and take transpose for each element. Okay, yeah, and you can further simplify this a little bit. When you have a CG transpose or AB transpose, this becomes what? G transpose, C transpose, and this becomes G to the power n minus 1 transpose and C transpose. Okay. So instead of checking rank of this column vector, you can also check the rank of this row vector now, right? Yeah. So it will be equivalent. Okay. Sometimes the writing of this one is probably easier. Really depends on how you formulate to this matrix. So let's take a look at. Yes. Yeah. Okay. Let's look at a very simple example here. Okay, let's say suppose that we have a very simple system, 1, 2, 3, 4. Right. Here is a simple second order system, and the output here is this. Okay, so we want to check the observability and controllability for this system right here. Okay, so this is just a purely application of the formula that we're going to use, right? Yeah. So first of all, let's check. So first of all, you had to identify which is which, of course. So this is our GHC. Okay. And let's take a look at the observability matrix. Controllability matrix. So the controllability matrix. This is second order. So here essentially your n equal to 2, right? Yeah. If you look at the formula, then that's basically GH up to 2 minus 1. So it's basically up to these 2, right? Yeah. So GH. Okay. And G is over here, H is over there. So the first column is H, which is 1, 2. Second column is G times H, so that you can find it out, which is 5, 11. Okay. And this matrix, if you use MATLAB checking the determinant of this one, and obviously this is not a 0, right? So 1 times 11 minus 5 times 2, which end up 1, right? Yeah, so the determinant is 1, and so the rank is, which means the rank is how much? How many? 2, right? So 4 rank, okay? And then you look at the OB matrix, okay? So let's try either way. You can try either way here. If we try the first one, this is CG. Okay. C is 1, 2. C times G is 1, 2 times this one here, which will give us 7, 8. So that's your OB matrix. Okay. And if you use OB transpose matrix, of course, it's going to be the transpose of this matrix here, results, right? Yeah. And you can calculate the determinant by determining the rank. 8 minus 14, so negative 5, so still not 0, so which is full rank at here. So both matrices are full rank, so the system is both controllable and observable. Okay, yeah, it's very simple. Okay, so here I have one final theorem right here, basically wanted to present here. Now we're talking about controllability, we're talking about observability, but we need to put this thing together. Basically, the question is, is there a condition such that guarantee the complete controllability and observability at the same time? So I'm going to give you a theory. Basically, what's the condition for complete controllability and observability? So a system basically both controllable and observable. Okay. So here's a theorem. If a system is completely controllable and observable, okay, if a system is completely controllable and observable, then there is no pole zero cancellation. In the pulse transfer function. Okay, yeah, in the pulse transfer function. This is actually basically a necessary and sufficient condition here. So let's take a look at how do we interpret this theory here. Okay, so there's no pole zero cancellation in the pulse transfer function, right? So this is the keywords here. There's a pulse transfer function. Another keywords is pole zero cancellation. Okay, yeah. So first of all, let's try to understand. First of all, let's just remind us of pulse transfer function. I mean, pulse transfer function basically is a function relating the output and the input. Right? That's your pulse transfer function. Now, there are different ways to derive pulse transfer function, right? You know, you can derive based on the closed loop system, okay, by looking at the blocks of the pulse transfer function for each block, and then you can derive the closed loop pulse transfer function. Or, for example, let's say if a system is given like this, if the system is given in a discrete state space model like that, right? You could also derive that. I think that we did this before. So if what you have is a state space model, then the pulse transfer function is simply just c times zi minus g to the power -1, then times h. That's your pulse transfer function. Okay? Yeah. So let's take a look example, and then I'll explain through the example. We'll explain what does the pole zero cancellation mean here. Okay. Okay, so suppose we have a system, okay, with a system matrix G and H, and here's G. So here's a G matrix, here's H, and here's C matrix. Okay? Yeah. Okay, before we proceed here, right? You look at the given system matrix, matrices G, H, and C. What does that remind you? Look at the G matrix here. It's in what type of format? Control canonical format, right? Yeah. And so does this H and C. So basically, you don't really have to do anything, because you look at this one, this format here, this is exactly in the control canonical format, right? So basically means the system is definitely going to be controllable, because you're putting it into the control canonical format, right? So so you could, of course, you can check basically by putting into this h g square h, because here n equal to 3, okay, and you'll be able to find, okay, so the rank of this matrix is 3. Okay, so this system is controllable, right? Okay.
The determinant of that always 1.
Determinant for this one, you mean?
Yeah.
Not necessary. Yeah. So let's take a look at the observable, right? Let's take the observable, and you do this one here, okay? Or you do C transpose, G transpose, C transpose, G square transpose, C transpose. Okay, that's observable matrix. Either one is fine. Actually, I shouldn't say this. This is not an equal, right? I shouldn't say the equal here. I should say this is OB transpose, right? Yeah. Okay. So you can choose either one of these, okay, to get the results. I think what I did, I used this one here. I got the results, which is which is this. Okay. So that's your observable matrix here. Okay. So now you can use the MATLAB to help you to calculate the determinant of this matrix, and you'll find that determinant of this matrix is equal to 0. Okay, you'll find it is equal to 0. So if determinant equal to 0, that basically means the rank of this OB is not 3, right? It's not full rank. It may be 2, right? Or maybe 1. Who knows, right? So that's fine. So which basically means the system is not observable. Okay? Yeah. Now, but the question here is why, right? We want to take a look into a little bit deeper issue here. Why this system is not observable here? So I'll leave that as an exercise here for you to do this. So essentially, here's your GHC, right? Let's derive. I want you to derive the pulse transfer function for the system, and which is the formula that I just wrote it down there. Okay, so that's your formula, to derive the pulse transfer function of the system. Okay. Now, if you carefully derive this everything, okay, let me find the original format. Yeah. If you carefully derive the pulse transfer function, okay, you will end up with a format like this. Okay, you end up with format like this. Okay, this one actually probably doesn't really tell you anything, because you look at this. Okay, that's a second order numerator divided by a third order polynomial, right? Yeah. However, okay, if you are if you're nerdy enough, you actually will be able to factorize the numerator and the denominator. Okay, the numerator is what? Okay, that seems to be pretty obvious, right? Yeah. And the denominator, you can further factorize it. Okay, it will become this. Okay, yeah. So now you see now, the system actually has what? Has a cancellation in it here. Okay, there's a pole zero cancellation basically. Okay, so the actual order of the system is actually what? It's not 3. It's actually 2. Okay, yeah. So this is basically one of the condition that we mentioned that it doesn't satisfy. So that's why it's not both controllable and observable. Okay, there's a cancellation at z plus 1 over there. Okay. This is also a concept which is basically called minimal. What is it called again? Minimal realization, basically. Okay. There's also a concept called minimal realization. Okay. Now, if you recall, when we started the state space modeling, and I mentioned about the choice of the state vectors, right? The definition for state vector is basically you need to choose a set of state vector that is minimal number that is able to describe the system information. So that's basically idea here, right? So in MATLAB there is a command called mini real. So there's a command called mini real. Okay. So what you can try is this. You can try. You have your GHC at here, right? You have a GHC here. So you can create the system. You can create a system using state space GHC. I think there's probably sampling time. There's probably not. I don't remember. Using SS state space command to create a system, and then you can feed this system into this mini here. Okay, and then MATLAB will actually tell you what the actual order of the system is. So it will cancel out. It will be able to detect that there's a pole zero cancellation. Okay. Yeah. So that's basically everything about the controllability and observability. Okay. Yeah. I think last time I mentioned, so for controllability is CTRB, okay, and for observability command is OBSV, okay, OBSV.
I think it's mini real, not mini real.
Oh, not mini real, eh? Probably you're right. Yeah, doesn't sound right. Mini real. Yeah. So. Actually, by the way, last lecture I was wondering what the CTRL is. CTRL is a Control C, Control V. That's why. Well, why it sounds so familiar. But anyway, yeah. Okay, so that's any questions? Okay, so let's continue now on a new topic. So we'll look at a new topic now, which is the pole placement. So let's take a look at the first part of this lecture, pole placement. So this is a controller design part now, right? Control design. This is basic control design in state space domain. Okay, using state space equation. Okay, so we're gonna we're gonna focus on the LTI SISO model. Okay, so linear time invariant LTI linear time invariant single input, single output at here. Okay. And the general state space model we're going to use, of course, is the same as before. Okay. Yeah. So, first step I'm going to do before we talk about this control pole placement. So here, if this is the system here, right? If this is the system, let's sketch the system using this idea of the simulation diagram, the idea here. Okay. So here is the sketching of the system here. Here's your input, okay, which is u of k, and then here is your output and x of k. Okay. Yeah. Now, if you look at the current structure here, so x of k comes from x of k plus 1, so you can let x of k plus 1 go through a delay here, okay, and that'll give you this x of k. Okay. Yeah. But then x of k plus 1 equal to what? Equal to g times x of k, and then plus h times u of k. So h should be here. So h times u of k plus this guy here. So these two adding each other, then produce x of k plus 1. Okay. So that's a simple simulation diagram, or diagram representing this system. As a matter of fact, this is something that you can use to construct this system in MATLAB Simulink. You drag block this block, right? And you can set this block G and H accordingly, and drag a delay block at here. Okay, then you construct. So that's basically your system. Okay, yeah. So for control purpose, right? For the pole placement at here, essentially. For control is you always try to find a way to produce this control input at here. How do we produce this? Yes.
I'm just double checking. So the input isn't a vector here?
Single input. So this is in this here I'm listing as a single control voltage. Yeah.
Right.
Yeah. Okay. So we wanted to somehow generate this control input to the system. How do we generate the control input? And then the control input can be generated by feeding back this output x of k at here, right? Yeah. So one simple way to generate the control input is this. You feed back this x of k, and then use that feedback, multiply, it's a negative feedback, multiply by a gain at here, okay, and then that is your actual, use that as your actual control input. Okay, yeah. So then basically here the point is, okay, it's like a closed loop, right? It's a closed loop here. However, okay, at least now we don't have that reference input at here. Okay, there's no reference input. This is basically just close the loop. Then what it means is the system, what it control is, it's gonna, the system has certain initial condition. Then you will try to, this system is designed is to try to bring the responsive system from the initial condition back to zero. Okay, back to zero. So this one here, we call that, it's a regulator. Okay, this is a regulator model. Okay, so regulator essentially this is to bring, okay, bring the system from x of 0 to 0. So your final state, desired state, is 0. Okay. And how, the question here is, how fast do you want it to bring back to 0, right? Yeah. And that's up to the design of this gain matrix K at here. Okay? Yeah. So let's take a look at this structure here, right? And how is that related to the concept of pole placement at here? Right? Yeah. So of course, I'll also write it down the objective. Okay, so given certain non-zero initial condition, okay, we want to bring this x of k, okay, any state back to 0, okay, by, of course, at here, by providing a suitable k at here, okay, providing suitable k. So, as I said, the whole point is essentially, here is your initial value. Let's see, I don't know, x of certain x of k, and you can start it here, and you can let it bring back to 0 like this. That's one way of bringing it back to 0, right? Yeah. Or you could bring it back to 0 like that. Okay. Yeah. So that's another way of bringing it back. And any of this response, it's up to the choice of the k at here, right? Choice of k.
Those three types, just like they had between
yeah,
undershoot,
exactly. Yeah. Overall, the bigger category is the 3 types. Yes. Yeah. But the ultimate purpose, the ultimate specific or requirement is, is based on, as you learn in continuous system, basically, what will be the overshoot, the percentage overshoot you want. If you don't want any overshoot, then that's like overdamped type of response, right? How fast do you want it to go back to 0? There's a time constant concept, okay? And what's the settling time that you want? So basically, how fast do you want it to settle into this 2% range around the steady state, right? So those things are all can be determined by appropriate value of the k at it here, okay? Yeah. So we'll look at the detail, of course. So the k at it here, okay, this is basically called control gain matrix. Okay, it's gain matrix. This is a design parameter, huh? This is a design parameter. So let's take a look at how the introduction of the k, okay, how the introduction of the k here affect the response of the system. Okay, yeah. Let's start from over here. Right? Let's start from original system equation. So now, you can see now your control input, right? Based on this structure is generated by multiply the k with x and put a negative sign there, right? Then I'll write down the new state equation now. Replace the u with negative k times x of k, right? Replace the u with negative k times x of k. So here is the new equation, okay, the new equation here. And take out the common factor, which is g minus hk, and then x of k. Okay. Okay. So if this is a system, let's take a look at the solution for the system here, right? So let's take a look at the solution. What will be the solution here? We start from x1 here, so that's g minus hk times x of 0. You can start from here, and then we'll start to iterate. Okay, start to iterate here. So then the second one will become square now. Okay, x of 0. Right. So you can iterate up to, let's say, x of k, and that gives us hk times k here, and x of 0. Okay, this is a solution, right? See that's the solution for this closed loop feedback system. Okay. Let's check out this solution here, right? Let's look at the solution. Remember, what's the objective, right? Objective is what? You want your x of k go back to 0. Okay, so remember that setup I showed you, right? So if you successfully implement this pole placement, and if you try to twist that, the top axis, okay, a little bit, if you twist it, you let it go, then the controller will try to bring it back. Okay, it depends on the key value. Bring it back to this equilibrium, which is 0 position, immediately. Okay, that's basically what the effect of this one should do. So if you look at this one here, if I want this one go back to 0, then what will be the condition that this whole thing this x of k will go back to 0? If you look at this thing here, right? So let me give you a simple example right here, right? Let me give you a simple example. Okay, if you recall in the continuous first order differential equation, right? This is a first order differential equation. Okay, yeah. And if you derive the solution, which is that's the solution for this system right here. Okay, yeah. So that's the solution for this first order differential equation, continuous one, of course. Okay, yeah. So for this one here, if you think about it, under what condition that this y will actually, the c value, right? The c is decided. It's determined. It's decided by what? By initial condition. Okay. Okay. And then say you can change that initial condition based on initial condition here. So if you want your y to go back to 0, then the a value needs to be less than 0, right? Yeah, negative value. So the transfer function of this one here basically is 1 over s plus a, right? So that explains your poles needs to be on the left side, right? Okay. So if I look at this system here, right? If I look at this system, think about a very, very simple system, not a multiple input, not a multiple dimension for the state vectors. Think about just the dimension, just one dimension, right? If it's only one dimension, this g minus h, this is not going to be a matrix. This is going to be what? Just single value, right? The single value. So if I want x of k to go back to 0, then this single value needs to be within a unit circle. Exactly, right? So, but of course, g and h system, you can't change that. Then the whole question here is you need to provide an appropriate k value such that this whole value is within a unit circle here, right? So that's the idea of this pole placement or the k value selection. Yes.
The kn is like the exponent k. Is that different than the gain k?
Oh yeah, you're right. Yeah, this is a different one. Yeah, this is absolutely good. So this should be a small k, right? Yeah. This is the gain k here. Yeah. Very good. Okay. Okay. Yeah. Sometimes it's hard to differentiate when you write, in handwritings. Yeah. Okay. So, and that can be also explained, basically when you have a pole here, so this a to the power of k go past 0, then the absolute value a needs to be less than 1 here, right? So in this particular case, of course, let's go back to general case. If this is not a single if this is not a single vector here, a single dimension here, then what we really want is, so basically, if the eigen values of g minus hk, right? If these eigenvalues of this g minus hk are within unit circle, okay, then this g minus hk to the power of k will go back to 0, okay? As k small k, as small k goes to infinite. Okay. So that's the point. So you need to choose a suitable k such that this g minus hk matrix eigenvalue are all going to be within unit circle. And the location of the pole, okay, or the location within the unit circle, which we'll look at in the next, maybe next week, will actually determine the type of response for the system here. So sometimes we not only just need the stability, we also need to satisfy a certain type of response, right? Yeah. So then often in time, you design a system based on certain requirement, and the requirement can be translated into the pole locations. So you can assume you have a certain eigenvalues, and these ones could be pre-calculated. Okay, so this can be pre-calculated based on specifications or requirements. Okay, so this can be pre-calculated, and once you have this one here, then you would know that I need my k value such that this whole system will have, will satisfy, will satisfy this condition here, right? So that's Zi minus this will produce, the determinant of that will produce the eigenvalues, right? Yeah. As a matter of fact, the whole right side here, right? This whole right side here, if you expand it, this is basically what we call the characteristic equation. Okay, characteristic equation for the closed loop system. I should say desired characteristic equation. Good. Yeah. So now let's dig into the details of this pole placement, and basically the idea is always, the objective now is, so how to find this K matrix. Okay, how to find this K matrix. Okay. Usually it's based on some kind of user specifications. Okay. Specification basically means, for example, as I mentioned, the percentage overshoot, rise time, settling time, or time constant. Okay, so these are the typical user specifications that you will give. Okay, yeah. There's a pre-given, right? And the given this one here, then you can calculate the gain matrix. Okay. Keep this in mind. Basically, this is how we wanted to find our gain matrix. First of all, let's have the guiding principle at here. Okay, in terms of the pole placement. So here's the theorem: the necessary and sufficient condition for arbitrary pole placement so the idea, you wanted to, okay, I don't want to be restricting myself just to that particular pole location, right? I really wanted to be able to place anywhere I want within the unit circle. So that's what we call arbitrary pole placement. Okay. And the condition for doing this, right, is that the system, okay, is completely controllable. Okay, it's completely controllable. So that's the condition for doing arbitrary pole placement. Good. Okay. So basically, this condition, actually what it tells you is, before you start to design a pole placement controller, the first step is actually what? To check the controllability. Okay. Yeah. So let's illustrate this pole placement, okay, through a couple examples here. First example, let's look at a double integrator. Okay, so here's a double integrator transfer function, right, representation. Okay. Double integrator is a very, I mean, mathematically it's a double integration, right? So integrating twice, okay, integrating one and twice, okay. If the input is acceleration through this double integrator, then you get what you get position, right? Yeah. But it's a very actually a common description for many systems. One type of system basically is if you have a, let's say, mechanical object, okay, with a certain moment inertia J at here, and you're driving, for example, if this is the motor at here, okay, and you're driving it, okay, you're trying to rotate this mechanical object, okay, so you apply a torque and you rotate this moment inertia at here, right? And it's a very, very simple system. Let's say you assuming there's no friction, okay? Assuming there's no friction, then based on your first year dynamics, then the torque must equal to what? The moment inertia times acceleration, right? Yeah, Newton's second law, basically, right? Yeah. So in this simple system here, the input is the torque and the output is the position, right? So you can derive a transfer function between the output position and the input torque. Then you get 1 over s squared. So that's a double integral, and then plus a j here, right? Yeah, j here. So that's double integral. So double integral itself is here. It's just a very simple representation, right? So let's say now you have this system here, and we want to design a digital controller for this system, okay? And we want to do a pole placement design, a pole placement controller for this system here. So first step is to discretize. So the first step is discretization. Okay, and you need to discretize it using that zero-order Hall equivalent approach, right? Yeah. So I will roughly go through this this process here. So if I look at we're going back to this system here. Here's system. If I look at the system, I can transform the system back into time domain. So that gives us y double t equal to u of t, right? That's your, so y double t, y times s squared give you y double t, and equal to u of t, right? Yeah. And then we can choose our state vector, state variables. I'm going to choose my first state variable is the position, and the second state variable is the velocity. It's a very common selection of the state variable. Then you can write down the continuous state space model, okay, and that gives you basically, I'll skip a little bit of detail here, you can try yourself. From the selection of the state variable here, you can write down the state space model for the continuous system. Okay. And your output y is basically 1, 0 times x of t. And here is A matrix, here is a B matrix. Okay. Then we're going to discretize this continuous system with a certain selection of choice of a sampling time, right? Sampling time. If you recall that in the previous lecture we did the exercise, so we want to discretize this into discrete model. Essentially, we want to obtain the G matrix and H matrix for the discrete model here, right? And the G matrix, if you recall, G matrix is equal to e to the power of at, and then H matrix is equal to the integral here, e lambda, and then b and d lambda. Right. So here are the formula basically for discretization to get a discrete state space model. Yeah. If you plug in the A matrix here, the B matrix here, okay, we'll find that G matrix is 1, T, 0, 1, and H matrix here is T squared over 2, T. Okay, so different sampling time will yield a different G matrix and H matrix. Okay, that's it. So that's the part, and then so setting up the stage for the next controller design, which is the pole placement we're talking about here. Okay. So we're designing a pole placement like what I said here. So basically, U equal to H negative AK times X of K. The K matrix is what we're looking for. So I don't know what the K matrix is yet. So let's select. Okay, just let this K matrix K, okay, equal to this vector here. So this is going to be a vector, okay, row vector, because you're going to use the K multiplied by the X, right? The X vector is a column vector, so this is going to be a row vector here. Then the control input is negative K times X of K, which is K1, X1 of K minus K2, X2 of K. Is that good? Yeah. So remember, the way we started is a very manual process. We didn't use any help in terms of deciding on the state variable. So we choose the first one position, the second one is velocity for the continuous system, right? Then in the discrete system, the x1, what's the physical meaning for x1 now? x1 of k, what's the physical meaning for x2 of k?
Should not still in position and velocity.
That's right, right? That's right. So this is the reason I think I emphasized a couple of times. Okay? Try not to use MATLAB to help you discretizing a system. You choose your, because the MATLAB C2D, okay, not necessarily will choose position velocity as a state variable. Okay? You should manually choose this, and then use MATLAB to help you do the computation. That's fine. Okay? Yeah. Okay. So given this negative Q1, so my idea here is I want to obtain a general solution for K1 and K2 at here. Okay. Yeah. So, and we can start to substitute. Okay. Start to substitute this U of K back into the original state equation. Okay. So that's G minus HK, right, equal to this, and K is over here. Okay, so K is over here. So G and H are over here, right? So this G and H. So substitute G, substitute H, substitute K over here, and you can calculate this matrix. And that matrix is calculated to be this. So this is the matrix G minus H at here. So that's a basically that's the closed loop system matrix, right? So when you close the loop, you get this system matrix at here. So the idea of this system is, of course, is we wanted to place choosing certain K1, K2, so the poles of the system or the eigenvalue of this matrix are within unit circle, right? Yeah. So let's take a look at what is the eigenvalues of the system here, right? Yeah. So we can try this. We can try to calculate basically the determinant of this Zi minus G minus Hi, the closed loop, and to obtain the desired characteristic equation. So Zi minus G minus H. Okay. So and then you let the determinant equal to 0. Okay. So substitute. If you substitute Zi here, this is basically Z 0 0 Z, right? Yeah. And then minus this matrix, and then calculate the determinant of the 2 by 2 matrix. Okay. So overall, you'll be able to simplify this whole thing, okay, into this expression. Okay, so overall, you'll get this is basically the closed loop characteristic equation. Right. So here you get, here is your closed loop, okay, the characteristic equation. Okay, so here's the closed loop characteristic equation here, right? And we still don't know what the K1, K2 is, because we haven't really specified what our requirement yet, right? Yeah. So let's say right now you as a designer, okay, then you said, okay, what I really want is I want my desired poles, okay, to be lambda 1 and lambda 2. Okay. So how these lambda 1, lambda 2 are coming from are purely based on maybe certain overshoot, certain sampling time, right? That type of requirements. Okay. So I'm going to keep it a general for this one here. Okay. So let's say you really want it. Let's say we want the desired poles to be lambda 1 and the lambda 2. Okay. So what does that mean? It basically is you basically want your desired characteristic equation. You want your desired characteristic equation to be Z minus lambda 1 and Z minus lambda 2 and equal to 0. Okay? Yeah, that's what you want, your desired closed loop characteristic equation. And expand this, you can get Z minus, here's lambda 1 plus lambda 2, Z, lambda 1, lambda 2, and equal to 0. Right? So now you get this square here. So now you got a desired second order polynomial. Okay? So here is a desired, right? Here's a desired. So let's simplify this a little bit here. Let's just say I call the coefficient here is P1, and then let's use a plus here. And then the coefficient here is a P2. Okay. So you got a desired here. Desired meaning you know it, okay? You have it, right? So this one here, this should be known here, okay? This should be somehow you can obtain, okay? And so it's your flexibility to design. Here's the known one here. Now here's what we call, this is your actual, right? This is the actual characteristic equation. Okay? So you want the actual one to be the same as the desired one. So you want the actual to be the same as the desired. So that basically means you want the coefficients of the polynomial to be the same. So that gives us two equations. So P1 equal to and then P2 equal to So P1 is known, P2 are knowns. And now two equations are here, so we can actually solve for K1 and K2, right? So two equations, you'll be able to solve for K1 and K2. So your K1 and here is 1 over solve it, and you get a solution. Okay, you get a solution like this. Okay. So that is a very manual process to derive the gains K1, K2 based on certain desired characteristic equation or based on certain desired pole locations, right? So you can imagine, of course, if this is a second order, so we can do this. This is not too bad, right? If you have a third order, fourth order, I think the manual process probably will be too much, right? So that's what the next we're gonna have is a more general, basically a solution for the pole placement. Okay, yeah. But this is a very good illustration for the second order system. This is especially in an exam setting, right? If I want to test your understanding of the concept, and I'll give you a very simple system, right? And the highest order is going to be a 2 by 2. You don't need to worry about more than dimension of 2. And then you can go through this manual process to obtain a desired gain here. Okay, so let's take a look at one more example here. Okay, for this example, and then I'm going to apply a certain type of design criteria now, okay, into this example. I'm going to start same as the previous example. So start with the continuous system. Here's a continuous system, transfer function. This is a system. Okay, here's a system, and you basically, this is a pulse transfer function relating input and output, right? Again, if you rewrite this system, this is essentially not much difference from the first system. It's a second order one. Okay. The only thing you can understand here is basically there might be a friction involved in the system, so that's why you see a plus, there's s squared plus s here. Transform that into time derivative, y double dot plus y dot equal to 10 times control input u. Okay. Choose your state, first state to be position, choose the second state so I should say this is x1 here, and then x2 is y of y dot at here. Okay, choose your second state is y dot, and we're going to use a sampling time t equal to 0.1. Okay, use t equal to 0.1 as sampling time. Then I'm going to now next step is to discretize the system. Basically, from here you can write down. You try yourself, okay? What is the continuous state space model? Okay, here is, so basically what A equal to and what B equal to. Try it yourself. This is going to be test. There will be definitely this kind of question in the midterm. Okay. Oh, by the way, midterm is coming up though, huh? March what? March 1st, next week, next Thursday. Yes. The midterm will just the first and second assignments, huh? Yeah. So derive this based on the selected state variable. Derive A and a B. Once you get to A and a B, and you can discretize the system using t equal to 0.1. Discretize that to get a discrete model. Okay, and this is not G, this is H. Okay, the G you will find, which is equal to 0.095, 0, 0.905. Okay, and then the h is equal to 0.048, 0.952. So I skipped a few steps. I think you should try to exercise yourself or look at the lecture notes. With the discretization zero-order whole equivalent, you get your G and H matrix, which is these two at here. Okay. So now, of course, your output equation, not much difference, is basically 1, 0, x of k. So now I'm going to try to do is to derive a pole placement controller for this matrix, which G and H are described here. Okay, so the negative feedback is this. So negative k1, k2, and x1 of k, x2 of k. Yeah. And similarly, you can get your actual, basically with any k1, k2, you can derive the actual characteristic equation. So let equal to 0, then you'll be able to get the actual characteristic equation. Yes.
X. So if in the equation u of k is equal to negative k times x of k,
yeah.
Is it supposed to be x of 0?
Here? No, this is a feedback, right? This control in general is always negative k times x of k. Yeah. And you plug this one into here, right?
Right.
Did I miss? Oh, there's h here. Where did the h go? Right? Yeah, you plug in the u over here, right? Yeah, you get your closed loop. And then you solve the determinant of this one here. You'll get the following. It's a little bit number-wise. It's hard to come up with a very integer number because we got a sampling time involved. So sometimes, it's better to keep at least 3 digits decimal there, okay, in order to be accurate. Okay. So you get basically a actual second order characteristic equation for the system, okay, involving this k1 and k2 at here. Is that good? Yeah. So, and now the next step is to select or determine what will be appropriate k1 and k2, right? Yeah. And you can actually use a fairly basically simple, say, okay, let's just use k1 equal to 0, k2 equal to 0, right? This is sometimes called the trial and error approach, right? Because you don't know what the combination of k1, k2 will give you, what type of eigenvalue will it give it to you, right? Yeah. So if a k1 equal to 0, k2 0, actually you can imagine what does that mean, right? If k1 equals 0, k2 equals 0, if you look at the solution in the system, so basically, what does that leave you when k1 equal to 0, k2 equal to 0? You don't have feedback, and within the bracket, you only have which term? The g term, right? Yeah. So you are only left with the g to the power of k, and g is part of the what? The system, right? The system here. So in this case, basically, your thing is, okay, I don't really want to design anything at all, and let's just wish our luck that the G matrix actually has eigenvalues both inside the unit circle, right? If that's the case, then you got a stable system. Still, you got a stable system, basically, right? Yeah. So let's take a look at this one. Right? If you set both of them 0, and you get, okay, you get a polynomial, which is this, right? The characteristic equation. Okay. Here's your characteristic equation. Then you can solve for its roots, okay, or the poles of the system, and you solve for this, and chances are you end up with a pair of complex conjugates, okay, number. So if you solve this one here, you'll get, in this case, you'll get a pair of complex number here, their conjugate, of course. So for any complex number, right, you can always write it into its what is it called again? It's this is called modular and arguments, right? Yeah, or the length and the angle. Okay, yeah. So you can always write it into this format here. Okay, and this whole thing, the thing here is readings. Okay, yeah. So you get, in this case here, you get a pole location. Okay, with this much of modulars with this angle here. So you can try to plot. You can try to plot these two poles within the unit circle. Here is your real axis. Here's your mx imaginary axis. Here's the 1, right? Yeah. So if you look at this one here, the 0.091 reading, that's fairly small angle, isn't it, right? So, and 0.954 is a value very close to the edge of the circle, right? So you're somewhere, probably one is over here and one is over here, right? The pole location. Okay, yeah. So that's actually not bad. You know, basically it's a stable location, right? A stable location. So, but the question, of course, this location may not be a very good location in terms of producing a desired response. Okay, yeah. Especially when you have a pole that is close to the edge here. So that means you have a very slow response, essentially, basically. Okay, yeah. So now from here, let's try the different, basically a different set of value. Now, basically, I don't really want my pole location to be here. I want it at a different location. Okay, yeah. In the next lecture, what we're going to cover essentially, we're going to cover a concept essentially here from the pole location, right? From the pole locations, what's the basically what is the corresponding damping ratio? Okay, and what is the corresponding time constant? Okay, so we're going to establish the connection between the pole locations and the corresponding damping ratios and the time constants. So that way, when you look at the pole location, you will be able to say, okay, so that corresponding to this much damping, and that corresponding to approximately that much of a time constant. So that tells you how much oscillation would you expect, and how faster that would you expect. Okay, yeah. So the connection here, basically, I will write down the solution for now, but it's a very simple one. I'll show you in the next lecture, basically, how we will be able to end up with this. So damping ratio, we generally use zeta to represent a damping ratio, and time constant, we typically use a tau for time constant. Okay, yeah. When you have pole locations in the discrete domain, okay, the damping constant, the damping ratio or damping ratio is approximately to be this. Actually, it's equal. So ln R over over this. So you have your R here, you have your theta here, and plugging this into this formula, you'll get your zeta value. Okay, the damping ratio. Okay. So in this particular case, if I plug in the R and the theta into this, I will get 0.46. Okay, 0.6. And then I can also get the damping constant, time constant, and time constant is related to this. Okay, so capital T over ln R will give you this time constant. T is a 0.1, so you get a 2.12 seconds. Okay, 2.12 seconds. So you, if you plug in, you get this damping ratio and time constant. If you look at this one here, so now this is a time. Actually, the third-year control system will help you now, right? when you see a damping ratio of 0.46, and that should actually tell you the response of the system, right? The response of the system probably going to be looking like what? Because this is 0.46, right? It's less than 1, so you should expect oscillation, right? And it's less than 0.5, so you should actually expect maybe quite a bit of oscillation, right? Yeah. So the response probably will be like this, right? Yeah. And then the time constant, 2.12 seconds. Basically, time constant, the definition is what? Is how much time it takes to reach not 90%, 63%. Yeah. So to reach the 63% of steady state value, right? So so basically, from here, how much time does it take to reach 63%, right? Here in this case, it's probably approximately 2.12 seconds. Okay, yeah. So that's the type of response you would expect with your choice of gain, feedback gain K1 and K2. That make sense?
Is that just the 1 over 2 point?
Hmm?
Is the 1 over 2 point of like the...
Yeah, it's basically we typically, if you look at this way here, right? If this is a exponential function, then here is, let's say, 63%. If this is 1 here, right? Then this time here, this is tau. Yeah. Good. So now the question here comes, okay, when you look at the results here and then you say, I don't think I'm very satisfied with this, and let's basically say I really want is, I want my desired tau to be 1 second. So I want it to be faster. I don't mind of the oscillation there, right? Just in case, just doesn't matter. So I want this tau to be 1 second here, and I will keep this one to be 0.46. Okay, yeah. If that's the case, then what will be the K1 and K2 for the feedback gain? Okay, yeah. So here it'll require you a little bit inverse calculation now, right? So this is the formula for damping ratio and the time constant. So if I look at the second equation, time constant here, if I give this one, then I can solve for the R here, right? I can solve the R. So your R is ln R equal to negative T over tau, and R equal to e to the power of T over tau. Okay. Yeah. Now plugging the tau 1 second over here, plugging the sampling time 0.1 in here. So this give you what? Gonna give you a 0.905. Okay. Yeah. And that's different now, right? See, originally it's 0.954, isn't it, right? Yeah. That's your R, okay? So we're still keeping this zeta here, though, right? Still keeping the zeta here, okay? Based on the first equation at here, okay? Based on the first equation, I can solve for theta square. So you can basically see, if you know zeta, if you know the R, then you can solve for theta, right? You can solve for theta here. So square both sides, and you can solve for theta square. So theta square equal to ln square R over zeta square minus ln square R here. Then you can solve for theta. So theta here will be 0.193 readings. Okay? Yeah. So you got a new R, a new theta, then form your desired. So basically, here's your desired pose, right? So Z12 will be 0.905 plus minus 0.913. Okay. So that's the desired pole location, and put it back into the A plus JB format, which is happen to be 0.888, and then plus minus J.173. That's the desired pole now. Okay, that's the desired pole. The desired pole, which basically means you have let's use lambda here, sorry. Lambda desired, then this is a desired characteristic equation, which is z minus lambda 1 plus z minus lambda 2. And you end up with z squared minus 1.776 z plus, yeah. Here's your desired characteristic equation. And what is the original general characteristic equation? This is a general, the actual, right? So you need the actual to be the same as the desired. So you need the coefficients at here to be the same as this and that, right? Yeah. Then you can solve for K1 and K2. So this time you solve for K1 and then end up with this much. And then this one end up with this much. So that's it, right? That's your calculated gains value. Then when you design your system, okay, when you implement a system, especially for the projects, it is very, very straightforward. So all you need to do, remember that orange block, you don't even have to change that, okay? So right, orange block, all you need is just add a gain block from the Simulink, drag a gain block, and enter the gains over here, and that's it. That's your pole placement controller. It's a regulator, right? If you pick the case appropriately, you run it, and then you will feel the resistance. You want to change that from certain value, they'll quickly come back, that kind of things. Okay. Yeah. In the next lecture, we'll present you a general formula for pole placement calculation of the gain, called the Ackermann formula. Okay. So, and I think we're only gonna have a lecture next Tuesday, and then the next Thursday we'll have the midterm. Okay. Yes.
If the first two assignments are only what's on the midterm, what's the cutoff lecture?
What's what?
The lecture.
Oh, the cutoff lecture. Good question. I need to double check. Yeah, but yeah, I'll send another email just to confirm.